The first paper this afternoon is going to come from Lutfi, who's talking about using machine learning in order to estimate traffic mix of buildings from stops data.
Thank you, Len. Good afternoon, ladies and gentlemen. Thank you very much, Len. I have it on good authority that Richard yesterday commended or mentioned Monte Carlo simulation. Yeah, great. Thank you. So, the question is, what is the new hobby horse then? Who can guess?
AI.
Machine learning, yeah, very well, yes. Thank you very much. Okay, so you'll be hearing about machine learning for the next couple of years, 3 or 4 years. So, anyway, started this research a couple of years ago. If you remember, we were talking about putting an accelerometer inside the car, inferring the stops, the acceleration, the position, the data, and the traffic, and from it, assessing the mix of traffic. So you can imagine Richard surreptitiously carrying an accelerometer, dropping it in the car, coming to pick it up 8-10 hours later, and then analyzing the data and knowing the traffic. That's really the aim of this. This year we have machine learning. Last year it was very much basic assessment and intuition. So this is a revision from last year, and the year before, and the year before, and the year before. So we measure the acceleration, integrate twice, and you get position. So you measure it with an accelerometer, and then you can actually infer position. So you know exactly where you are in the building just by integrating twice. So use the same building, and this is something I will generalize later on. So we'll talk about different buildings. But for now, we're concentrating on one building. So this is the same building from last year. We assume we have 13 passengers in every round trip. So every round trip we deliver 13 passengers, 10 floors, 8 occupant floors, and 2 entrance floors. And I assume you're familiar with the concept of an entrance floor. An entrance floor is a floor by which you enter or leave the building. Ground floor, basements, and so on. An occupant floor is a floor from which you can't leave the building. You are in the building. So that's an important distinction between an occupant floor and an entrance floor. And it's the basis for defining what incoming, outgoing is. We have 2 entrances. We borrow the Elevate terminology, entrance bias. So the basement, 30% of passengers enter from the lower basement, 70% enter from the ground. And in Monte Carlo simulation speak, we repeat this 100,000 times. There's entrance floors. So traffic circulating here will be inter-entrance. Traffic circulating here will be inter-floor. Traffic going from entrance to occupant is incoming, and leaving is outgoing. Important terminology. Let's have a look at these. What would you call case 1?
Pure up peak.
Great. So that's pure up peak or incoming. Second one? Down peak. Case 3, that's lunchtime. I don't know what you would call it, interfloor, pure interfloor, pure interfloor, meetings and so on. This is all fictitious. It's all fictitious, apart from the last one. Case 4.
Two-way.
Case 5. It's a mix. It's interfloor. Well, balanced. Would you call it balanced? Or would this be balanced? Maybe we should, yeah, that's balanced two-way. And this is general case. So we've assumed inter-entrance. Some people feel inter-entrance is irrational. Who feels inter-entrance is irrational? Okay. Some people say, no, inter-entrance is not irrational. You can't have people moving within car parks. Why would they do that? I don't know. But it's nice. It makes the math look nice. We have 4 numbers instead of 3. So instead of actually going and collecting data manually, we can generate the data now. So you press the button, within 7 seconds, you have 1 million cases, different cases. We need to generate the data so we can do machine learning. Machine learning needs data to learn on it. So this is the data generated. You can't read anything of that, but it's a triangular table. And what we change, incoming traffic, so from 10% to 100%, and 0, outgoing, And because when you have, for example, 30% and 70%, you can't have any more. That's why it's triangular. And then once you know what the incoming is and the outgoing is, you can deduce what the interflow is. So 10% outgoing, 0% incoming, you will have 90% interflow. So the third number, assuming there's no inter-entrance, you know what the number is. And this is a signature. So with 0% incoming, 0% outgoing, we only have interflow. So all the stops are on the occupant floors, which makes sense. So that's 6.5, 6.5, and so on. And this is another signature. This is a generic signature, for example, 10%, 10%, 80%. So that's a nice way to generate data. And all that data is populated here. You can have a large number of combinations, but we've picked 10%. So results. Let me go to one which is a bit clearer. What is that shape? What would you call this shape? A sail, yeah? Good, yes. If I flatten it out, what would it look like? Probably a triangle. So it's like a triangle which has been bent. And we have x-axis, y-axis, and you have like a piece of cloth or a surface. And that's where machine learning I can give this data to a machine learning, and it can learn that shape without knowing the formula. So this one, for example, is down stops on entrance floors. Up stops on entrance floors. Up stops on occupant floors, and down stops on occupant floors. And you can see basically the same triangle, but in 4 different combinations. And there's a summary. So basically, every round trip, we have a signature. We've gathered that data. What we can do now is train the machine learning on it. So by knowing incoming, outgoing, and interflow, it can come up with this number. We invert it, and we have an equation. We didn't actually derive this equation analytically. We used machine learning to derive it. And what this is saying, if you want to know what the incoming traffic in a building is, you have to know what the up stops on entrance floors are, down stops on entrance floors, up stops on occupant floors, and down stops on occupant floor. I didn't derive this equation. Machine learning gave me this value. So you start getting a feeling for what machine learning is. It can allow you, without knowing any equations, you can actually get the data and derive an equation. Another equation is for incoming, outgoing. So sorry, this should be an O, outgoing, and the same for interflow. We've been lucky with these. We have 1 dimension, 2 dimension, and we plot on the 3rd dimension. What if we had three variables? What could we do? Can we visualize it? We can't visualize 4 dimensions, can we? It becomes a hypothetical graph which we can't see. You can visualize this nicely because it's 1 dimension, 2 dimensions, you plot on the 3rd. But if you had 3 variables, it's 1 dimension, 2 dimension, 3 dimensions, and you plot on the 4th, and you can't see it. And that's the dilemma of the ants. The ants live in a 2-dimensional world, yes? It's difficult for an ant to see, so they can move on a plane. In the same way, a train. How many dimensions does a train have? Between London and Kettering, it's a line. So we just have 1 dimension. We say it's 50 miles away from London. It's 60 miles away from London. How many numbers do I need to describe the position of the train? 1. So a train really lives in a 1-dimensional universe. An ant lives in a 2-dimensional universe. So they can move on a surface. They can't fly, move out. They can't move outside that plane. If these ants, if a sphere came down here and then crossed this surface, what would the ants see from the sphere? Would they see the full sphere? What would they see? They would see a circle. What happens to the size of the circle as this sphere goes through? It starts from a dot, gets bigger, and then it gets smaller. So did the ants see a sphere? No. What did they see? They saw the projection of the sphere on their dimensions. This is just trying to give you a flavor of what a 4-dimension, what the difficulty of understanding 4 dimensions. Unfortunately, there was a very nice slide, but I must have forgotten to put it. What do we call this, this shape? In our saddle, it's a saddle, yes. So that's an example of a 2-dimensional space. We have X, we have Y, and then we plot on the third. As the number of variables increases, machine learning doesn't worry about that. It needs a number of variables, 5 or 6 or 7, as long as they are orthogonal. Where's Jonathan? Orthogonal. The definition of orthogonal would become very complicated. But that's the idea. So we could have 4 dimensions, machine learning, traffic, and then we can actually learn from that. It's difficult for us to visualize, but that's not a problem. So let's conclude, and further work is very important because this was done on 1 building. What would be really nice if these 4 shapes which we saw could become generic for any building. So work is being done now on actually generalizing this on 10 different types of buildings with a number of different floors. So this could become a universal equation which we can apply to any building, rather than actually understanding the type of building. So to summarize, we want to get to a stage by which we can put an accelerometer inside the car, find the number of stops, apply it to machine learning, calculate the mix of traffic, and then we can find the relationship between the number of stops and the mix of traffic in the building. The further work, this would be really a nice piece of work from this. This was based on 1 building. As the type and size of the building changes, will these results persist? So we have a universality. And to do that, we need to do what is called normalization. We divide the number of stops by the number of floors. We have a number from 0 to 1, and then we can apply it to any building. And that's the purpose of the next stage of research. Who found this surrealist, the 4 dimensions and 5 dimensions? Raise your hands. Surrealism. Who's the father of surrealist art? The Persistence of Memory, 1931. And that brings us to the end of the presentation. Thank you very much.
We probably have time for perhaps just 1 question. Does anybody have any questions? If not, it's a subject for discussion this evening, I'm sure. No? Lutfi, thank you very much.
Thank you very much. Thank you.